Hello students, welcome to the class. So today we will do the NCERT Examplar questions of the chapter 5 Thermodynamics. In this session we will be covering 6 questions, okay? 7 questions. So it will be 2, 7, 14, 23, 30, 31 and 42. So this is the disclaimer. Now our today's objective would be of course covering the questions of the NCERT Examplar, but I have framed the question in such a way so that you get a taste of each and every type of question that can probably come in the exam, right? Here is the first question. Which of the following statements is correct? Now, there are 4 options given. The presence of reacting species in a covered beaker is an example of open system. The second one is that there will be exchange of energy as well as between the system and the surrounding in a closed system. The third one is the presence of reactants in a closed system made up of a copper would be example of closed system. And the fourth one is that if you take a system in a thermos flask, then it would be example of a closed system. Now, it's a very basic one. Directly from the types of system, we have seen that we have 3 types of system on the basis of exchange, which are open, closed, and isolated. If you know the definition, you are good to go with this question. Your time starts now. Just analyze each and every question and look for the correct statement. Okay, your time is up. So the correct statement will be that the presence of reactant, if you are taking them in a closed vessel, which is made up of copper, then it would describe a closed system. You know it very well what a closed system means. There you can only exchange energy and not mass. So is it true that your copper vessel is an example of closed system? Yes. Let us see how. Now, if I take a vessel which is made up of copper, then it can exchange energy. And the reason behind this exchanging is that a copper is a good conducting material. We know it is a metal and it can conduct both heat and electricity. That is the reason it can conduct this heat and thereby exchange energy. Therefore, we can say that since a closed system is one which can exchange only energy, hence a system imagined inside a copper vessel will be also a closed system. Moving on to the remaining options. So if I talk about the open system, it is a system in which both matter and energy can be exchanged. You can take very simple examples like a cup of tea placed in an open environment. So that would be a very approximate example for your open system. Last one is your isolated system in which we can neither exchange energy nor your matter. And the quick example of that would be a thermos flask. You must have seen a thermos flask which is used to keep the water at a certain temperature, right? So if you want a cold water, you put it in a thermos flask, and after some time, you will notice that the rise in the temperature is not that much significant or not that much usual. Similarly, we can observe the same thing for the hot water as well. Then here is your next question, question number 7. You have an adiabatic process, okay, and no transfer of heat takes place between the system and surrounding. Then you have to choose then which of the following option of for free expansion of an ideal gas under the adiabatic condition, right? So if you're taking an adiabatic condition and you're saying that no transfer of heat is taking, so as we know, adiabatic process depicts the same, and we are also saying at the same time that this is an example of free expansion. So what can be inferred from this statement? Your time starts now. Think about the change in temperature, the work, and the heat. So let's see what will be the correct answer. We know it very well that for a free expansion, if you are taking an ideal gas, see, it is clearly written that you are doing a free expansion for the ideal gas. Now for the ideal gas, the free expansion results in zero work done because there is no external pressure which is present, and we know that the formula for work done is minus P external multiplied by change in volume. As there is no you can say external pressure because it is expanding freely without any exertion. Therefore, in this case, the work done will be zero. Next thing, the question is itself saying that it is an adiabatic process and defining the same, that no transfer of heat will take place. So, Q will be also equals to zero. If these two things are zero, can we say from the first law of thermodynamics that the internal energy change will also be zero? Yes, it's very obvious as your Q and W both are zero for the process. So, your change in internal energy is also zero. If that is true, then we can go back to an important formula of the internal energy calculation, which is CV delta T. And we also know that delta T is also a state function. So, if your delta U is 0, then we can also say that delta T will also be equals to 0. Right? Therefore, we can finally conclude that for a adiabatic expansion of an ideal gas, there is no heat transfer, okay, given in the question, no work done because it's a free expansion, and no change in temperature as the internal energy change is zero. Then here is your next question. Which of the following is not true? Delta G is zero for a reversible reaction. Delta G is positive for a spontaneous process. Delta G is negative for a spontaneous process. And D, delta G is positive for a spontaneous reaction. Your time for this question starts now. How can we solve it? It's very simple. You just have to look at each statement and look for the case for spontaneous process. That what would be the value of change in Gibbs free energy? So your time is up. Okay, let us move on to the answer. The correct answer will be that delta G is positive for a spontaneous reaction. So it's a very simple one. We have already studied that Gibbs free energy change is the criteria for defining the spontaneity at constant pressure and constant temperature. And this is useful because it does not take into consideration about the surrounding. It depicts the spontaneity of a reaction, unlike our entropy, with the help of system only. Now, what was the condition for that? It was very simple. We arrived at three different situations. First is, if delta G is negative, then we said that, okay, the process will be spontaneous. The second situation is, if it is not less than 0, instead of that, it is greater than 0, then in that case, we'll call the process non-spontaneous, and that is the case for our option number B. The last thing which we know is that delta G is 0. And when it is 0, when your reaction reaches the equilibrium and there is no Gibbs free energy change after that situation. Therefore, we got the Gibbs free energy change is equals to 0 at equilibrium. Here is your next question. The net enthalpy change for a reaction is the amount of energy required to break all the bonds in reactant molecule minus amount of energy required to break all the bonds in product molecule. So this is basically given for the enthalpy change of a reaction in terms of bond energy. Now, you have to determine that what will be the bond, what will be the enthalpy change for the following reaction, in which your hydrogen is reacting with bromine to give us hydrogen bromide. We have some data as well. So the bond energy of H2 is given as 435 kilojoule per mole. Then we have for Br2 as 192 kilojoule per mole. And lastly for HBr we have 368 kilojoule per mole. Your time to solve this question starts now. let's see what is the correct answer. The correct answer will be minus 109 kilojoule per mole. So this will be your enthalpy of reaction. How I will solve it? Very simple. What else is given in the question? So the bond enthalpy of dihydrogen, your bromide molecule, and your HBr is given, right? So this is the first set of information, and we are also given along with the equation where we are saying that this is for the formation of HBr from H2 and Br. How we'll do it? If I talk about the net enthalpy change for a reaction, then it can be written in this way in terms of bond energy of reactants minus the bond energy of products. Here again I am repeating this part. We have already talked about this in the theory part. Whenever you are taking for the bond energy part, then you take it from the reactant minus product side. And this is the only case we do this thing. Why is it so? Because bond energy is basically the energy required to break 1 mole of bond. Okay, so this is good because in reactant side the bonds are broken. But if you are adding with the product side bond energy, but we know that in the product side the bonds are formed. Therefore, we have to take a negative sign against it. Putting all the values and taking the HBr concentration as 2 multiplied by the bond energy of HBr, because the contribution in the equation is 2. It will give you an enthalpy change for the reaction as 109 kilojoule per mole. So this is your answer. Next question. A sample of 1 mole of monoatomic gas is taken through a cyclic process of expansion. A compression for as shown in figure, what will be for the delta H of the reaction? You have to basically determine it for a whole cycle. Your time starts now. Just remember one thing, that your enthalpy changes state function, and this process is simply looking like a cyclic process. So the correct answer will be that the enthalpy change will be equals to 0. How we are saying it? Very simple. We know that the enthalpy change for a cyclic process is always equals to 0, and that is always true. To understand this thing, let us take a simple example of the same. So we are taking this diagram as the example. What you can say, that we are starting from 1, moving on to 2, then coming on to 3, and then again going on to 1. Now we can easily say that if your function is state dependent, then it will give you what? The same value for different state at a given pressure and temperature. So we got delta H1, delta H2, delta H3. Therefore, you can calculate the delta H as 0. Is it clear? Again, I am repeating it. Since your enthalpy change, the enthalpy change is to be calculated, and this process cyclic, we know that for the cyclic process, the state functions are taken as 0 because enthalpy is a state function. Therefore, we keep that delta H is equal to 0 for the given reaction. Our next question. At 298 Kelvin, Kp for the reaction N2O4 gases giving us 2 NO2 gases is 0.98, right? So Kp is given. You have to predict whether the reaction is spontaneous or not. Your time to solve this question starts now. You have 10 more seconds. Okay, let's see what is the correct answer. So the correct answer will be that the reaction will be non-spontaneous. So it's a very good one. Okay, so this question is very good. How? Let's see. So you have to go through the equilibrium also, and you have to go through the thermodynamics also. It is an integrated one, and we have already studied about this thing. Now for the given reaction, which is dissociation of N2O4, the Kp value is given as 0.98. then temperature is mentioned at 298 Kelvin. What we can say that from the formula delta G naught is equals to minus 2.303 RT log Kp, we can calculate the value of delta G. So we have done that same. See, the value of R is given, the value of your T is given, and we are taking ln 09.8. You can take either of them. Either you can take minus 2.303 log 0.98, or you can take ln 0.98. This will give you your final value of delta G naught as 50.05 joule per mole. Now this value is clearly positive. Therefore, the reaction will be non-spontaneous. So it's a very easy one, right? So we already have the value of Kp. We calculated the value of delta G naught. Hence, we got the value in positive term. So the reaction will be non-spontaneous. And this was your question. You have to determine the spontaneity of the reaction. Next question. The value of the enthalpy of formation for the ammonia is minus 91.8 kilojoule per mole. Now you have to calculate the enthalpy change for the reaction, which is simply dissociation of ammonia into nitrogen and hydrogen. Your time to solve this question starts now. Okay, your time is up. The correct answer will be plus 183.6 kilojoule per mole. How will solve it? What are the given things? We are given with the reaction, which is dissociation of ammonia. Then for this reaction, a corresponding reaction enthalpy is given, which is enthalpy of formation for ammonia. And it is given as minus 91.8 kilojoule per mole. So, what we can derive from here? For that, you have to know two things. Okay, for the derivation of the information from the delta H formation, you should know two things. First is that the nitrogen molecule will have an enthalpy of formation as 0 because it is present in the standard state. And same thing can be said for the hydrogen molecule as well. Now, if these two things are true, then what we can write for the enthalpy change of the formation of reaction? It's very simple. The reaction starts from the ammonia and ends at the nitrogen and hydrogen. So you will write it in terms of products minus reactant, delta H naught formation of products minus delta H naught formation of reactants. Both of your products are present in the standard state, so they will be having a value of 0. Whereas for the formation of your ammonia, the value is given as 91.98. If you calculate this thing, you will get your final value as plus 183.6 kilojoule per mole. Is it clear? It's a simple one, right? You just have to know that what is the enthalpy of formation and how you can incorporate the same in the enthalpy of a reaction. And the second important thing I would say is that the enthalpy of reaction for the standard state is taken as 0. Likewise, we are taking it for the nitrogen and hydrogen. So this is your final answer. So this was all for today's class.